In this unit, we discuss continuous random variables. I will once again beat you over the head with the definition of a random variable. It's a variable that can take on one of several realizations, and each one of those realizations has a likelihood of occurring. And continuous random variables are measured on a continuous number line. Continuous random variables are especially useful in helping us understand the performance of processes and systems. We can model the time to failure for each of the individual components in a large system, along with their time to repair, to understand the downtime of the system. Or we can model consumer demand per week to understand how many component parts we need to purchase from suppliers, and we can model the time required for a supplier to produce and ship our order, thereby enabling us to estimate the probability of meeting demand given some amount of lead time. We could also model the usage of electricity in a geographical area, giving us an idea of how to design a power grid. All of these values involve uncertainty, and all could be modeled with continuous random variables. The probability distribution function, or PDF, of a continuous random variable y is referred to as f of y. We calculate the probability of an interval as the integral of f of y evaluated on that interval. That is, we calculate a probability of an interval as the area under the PDF between the bounds of that interval. That probability, of course, has to be between 0 and 1, inclusive of 0 and 1. And the total area under the curve, or the sum of the probabilities of all mutually exclusive and collectively exhaustive intervals, is 1. And the probability of any particular realization of the random variable is 0. Hence, we keep talking about the probability of an interval. The expected value of a continuous random variable is the integral of y times f of y, evaluated between the lower bound and the upper bound of the distribution. The variance is the expected value of y squared minus the expected value of y quantity squared. We talked about a few particular continuous probability distributions. The first was the most famous of all, the normal probability distribution. The normal distribution describes a random variable that extends indefinitely in both the positive and negative directions, and it's centered about its mean value. Actually, its mean, median, and mode are all the same. The distribution is symmetric, so the median is equal to the mean, and the most likely value occurs at the mean as well. The normal distribution has two parameters, mean mu and standard deviation sigma. Mu describes where along the horizontal axis the distribution is centered, and sigma describes the dispersion of the distribution. To find the probability of an interval of a normally distributed random variable y, we convert y to a standard normal distribution. That is, we represent the distance between a realization y and mean mu in standard deviation units. The z-score is y minus mu divided by sigma. We also talked about the exponential distribution. The exponential distribution is related to the discrete Poisson distribution. Both use lambda, a rate of occurrence per an interval. A Poisson random variable measures the number of occurrences given the rate lambda, while the exponential distribution measures the interval in between occurrences. For example, if we have a rate of component failures per year, the Poisson distribution would count the number of failures in a year, while the exponential distribution would measure the years until the next failure. Counts are discrete. The interval is continuous. Also, the interval must be a positive number, so the exponential distribution is truncated at 0, and it extends indefinitely in the positive direction. Its shape is dictated by the one parameter, lambda. We touched on a few other continuous PDFs, including the continuous uniform distribution, the Weibull distribution, the gamma distribution, and the triangular distribution. But there are plenty of others. The log normal distribution, the Rayleigh distribution, beta distribution, the Dirichlet distribution, and so on. What distribution should we use? First, collect some observations of a random variable that describes a process or system. Plot it with a histogram, and see what shape it has. If the data look like a bell curve, maybe a normal distribution is a good choice to describe that random variable. If the histogram has an exponential decay kind of pattern, maybe an exponential distribution is a good fit. We'll talk about some of the ways to determine the fit of a distribution later on in the course. For now, let's focus on the properties of each distribution and how to calculate probabilities of intervals, and we'll pick up some goodness of fit characteristics later on in the course.